Yeah, okay, thank you. I'm very glad to contribute to following Charlotte about how we can make something useful from CO2. And actually, this was also my comment earlier during this meeting when I discussed with Kyle Harper that indeed we should not decarbonize the planet, because the planet is very, very carbonized and will be carbonized for certainly ever. So defossilization is clearly a better word. And in fact, that's what is shown here. I mean, I will go very fast because Charlotte said this before, but today, everything, I mean, producing energy, and here you have all the fuels and petrol, gas, and so on, but also you have 10 to 15% of what we use as a fossil carbon to make the products of the chemical industry. The most important one is being the polymers. And the question is, of course, when we will get rid of these fossil fuels, we will still need all these carbon materials. And in particular, the polymers, but not only the polymers, but any bulk chemicals, olefin, aromatics, methanol, specialty chemicals, polymers, plastic, pharmaceuticals, solvents, detergents. So we will need still all these compounds. And the question is, where do we get the carbon from? And I mean, we have no choice. I mean, it will be here, biomass, waste, and CO2. It will be actually very difficult to do that at the level, at the requested level. So, I mean, it's quite clear. And actually, the International Energy Agency is telling the same. In 2050, we will still continue to use probably huge amounts of oil and gas. But we try to do our best to move towards these carbon sources. And CO2 can be an alternative renewable carbon. Of course, if we capture it, I will not talk about capture. I anticipate that some people will take care of that, and I will have massive amounts of CO2 to transform it. So to make these kind of compounds, or also to make what we call e-fuels and e-methane and so on, because part of the energy also will be carbonized. So we need to also make this kind of compounds. So there will be, and Charlotte showed an example, but I think there will be a great revolution in organic chemistry where we'll move from the standard petrochemistry, with fossil fuels being the feedstocks, towards producing almost all of our carbon compounds, organic compounds, by combining resources from the biomass, by optimizing many different processes like fermentation, methanization, gasification, pyrolysis, liquefaction, Fischer-Tropsch, and so on. And on the other hand, also using renewable energy to electrolyze water, CO2, hydrogenate CO2, also combine to give all these products. That's the challenge, and that's what we, as chemists, many chemists are trying to achieve. In my case, what I will tell you a bit about one of these key strategies to do something useful with CO2 is electroreduction of CO2, with the hope we can make hydrocarbons and alcohols. I mean, the advantage of this strategy is threefold. I mean, the first one is, of course, you capture CO2 and you put less in the atmosphere. The second is that it's a way to store intermittent energies into stable chemical form. And the third application is that, of course, you produce useful carbon compounds for the industry. So the principle is here. We need to design this machine that we call an electrolyzer, where you put the CO2 that you have captured, you put water, and you try to make these two molecules to react together. It's very difficult because they are very stable, and for that you need energy. So you implement some energy into this machine, which is obviously renewable energy, wind energy, or solar energy. And by doing this, you make CO2 and water react together, producing all sorts of molecules. And these are feedstock for plastics, feedstock, fuels, pharma, specialty, and so on. That's the principle. And I want to give you an example of a product we are interested in, which is ethylene. I mean, ethylene is the top one chemical product in the chemical industry. It's close to 200 million tons per year. And of course, you understand why, because it's a precursor of a lot of polymers, the first one being polyethylene. And today, it is produced by cracking, steam cracking of naphtha or saturated hydrocarbons, high temperature, and it needs a huge amount of energy. It produces a lot of CO2. So as for many industrial processes, there is a need to revisit these processes and shift to less CO2 emitting and less energy consuming processes. And that's what I'm talking about. So the question is now, if instead of starting from oil, we would start from CO2. To get to this molecule, basically we need CO2, electrons, and protons. So that's why I mentioned why we need CO2 to react with water, because protons are coming from water, and the electrons are the electricity provided by the solar panel or the wind machine. The problem is that it's extremely difficult. Actually, if it was not, we would already have our planes flying with this, what we call synthetic fuels, e-fuels, but that's not the case. There are many problems that have been addressed actually quite recently, and I want to show you why it is difficult. First problem is that CO2 is very little soluble in water. So, as you know, kinetics are related to concentration. So very low concentration of CO2 in water means very low efficiency in terms of kinetics. I will show you that recently the design of electrolyzers has been changed to address this question. And in fact, you will realize that in this field, even though there are many basic fundamental questions about catalysis, mechanisms, and so on, there is also a real need to get into purely technological problems. And I'm very lucky because I have here in my lab at the Collège de France collaborators that like to make machines and not only to make DFT calculations. So the principle here is that now instead of solubilizing the CO2 into water, we design, it's quite complicated, but we design an electrode which we call a gas diffusion electrode in which the substrate CO2 comes as a gas, not as solubilized into water. And the reaction takes place at the interface between the catalyst layer, the gas CO2, and the liquid which provides the protons. This is the key thing, and we call this electrodes, gas diffusion electrodes, and flow electrolyzer, because the CO2 is flowing to react at the surface of the electrode. We have developed some electrolyzer together with a startup company, Sphere, actually coming from one collaborator from Jean-Marie. And these cells are now commercially available. I mean, we have contributed to optimize them. I mean, they are very nice. And this has been very important. And as you can see here, we can get very high current density. This is remarkable because, I mean, 10 years ago, we were two orders of magnitude lower. So it's a great improvement thanks to this kind of approach. The second problem is the problem of selectivity. Of course, if you want to do ethylene from CO2, you like to have 100% selectivity, having only CO2, only ethylene. The problem is that you have very few metal catalysts that can do this chemistry, CO2 to ethylene. In fact, if you look at this table, I mean, all metals have been tested. So you will not make any discovery in terms of trying a new metal. They have all been tested, and the outcome of this is quite amazing. It is amazing because only one metal is capable of doing carbon-carbon bond formation, CC coupling. And you have realized to make ethylene, you need 2 carbon, and you need to make a carbon-carbon bond. And there is only one metal able to do that. It's copper. All other metals, they do either hydrogen, which means that since you have protons, you have proton reduction to make hydrogen. They are unable to do CO2 reduction. So, of course, they are never used. Some are only able to do reduction of CO2 into CO. Some are able to do CO2 reduction into formic acid, but only copper is able to do that. It's amazing. I have no time to explain why. It's nice in a way because then you know where to go, but it's very bad because millions of people in this field are going to do the same thing. So the competition is huge. And it's bad also because we would like to have more possibilities, but we have to deal with copper exclusively. So copper is doing all sorts of compounds, products, methane, formic acid, CO, ethylene, hydrogen, and so on. So how to direct the reaction towards your favorite product? I want to show you different approaches quickly, what we have been doing recently. This is a funny story where really we were inspired by this diving bell spider. It's a very nice animal that has on the abdomen some hydrophobic hairs called a plastron. And this spider is able to live either in air and in water, and can spend a lot of time in water. And the principle is that thanks to this plastron, the spider collects bubbles of oxygen and can respire on oxygen inside the water. And this is because this is hydrophobic and oxygen goes there. So we asked whether we could do the same with CO2, which means that here the abdomen will be the surface of the electrode. We would put some hydrophobic hairs on the electrode, and we should accumulate CO2 there and favor CO2 reduction. For that purpose, again, I will go quickly. We developed a porous dendritic copper material that we have published in several papers. I have no time to explain how we got it. It's a very nice material with very high density of active site, which allow efficient mass transfer. So it's a very nice catalyst. And here, what we have done is that we have modified the surface of this electrode by attaching hydrophobic hairs. In fact, is a thiol for binding to copper with long hydrophobic chain, and you see here the difference between the material without the modification and the one with the modification. And without the modification, you have essentially hydrogen production because you have too much protons. As soon as you add this modification, here in blue, you have ethylene formation. So this is to show you that even though you have only one metal, you can play with the surface of the material to greatly modify the selectivity of the reaction, and this is very interesting. We've made the thing also. So the key is to control. What we are doing is that to control the selectivity, we use molecules. Actually, here you see a kind of multidisciplinary approach with combined molecular chemistry and solid chemistry. By this combination, we believe we can tune the selectivity of the reaction by inhibiting some reactions. And this is another example in which, for example, you see here, by adding this molecule on top of the surface of the copper material, as it is drawn here, you move from a catalyst that made a lot of carbon monoxide and ethylene to a system that is very selective for formic acid. Formic acid is also an interesting product for if you can make it from CO2. But this is just to show you how sensitive the surface of a catalyst can be and how you can play and try to understand how you can do that. Oh, this is an explanation too complicated. The second, this is the third. I mentioned the solubility. We try to solve that. The selectivity, you have seen some ways to address that. The third question, the carbonate issue. What is it, this story? It's probably the big problem of CO2. It is very simple. Yeah, it is very simple and at the same time very difficult to solve. When you do the reaction between CO2 and water in the presence of electrons, you generate hydroxide. And hydroxide is a very bad product when you do CO2 reactions because it's very good at reacting CO2 to make carbonate. So a large amount of CO2 is going to be converted into carbonate, and this is not useful because you want to do something else. You want to do ethylene, ethanol, and so on. So this is the reason why, in general, you have low CO2 utilization efficiency. So when you reduce CO2, you have OH minus that are generated as well. You make carbonate. Furthermore, you can have carbonate crossover through the membrane. And since you generate protons here, you generate CO2 here that is mixed with oxygen, so it's a mess. It's a mess, it's a big problem. And furthermore, you degrade by having this carbonate in the electrolyte, you degrade it. And as you can see here, a major cost in this electrolyzer is the regeneration of the electrolyte. So how can we solve the problem? There are two ways. I will show these two ways. The first one is to go to acidic conditions. This is a crazy solution if you think about it, because you now put in the electrolyte a huge amount of protons, and what they do, these protons, they do mainly hydrogen. So in most cases, you do hydrogen. But we have succeeded to, and this is a very recent work, and different labs have worked along this line. It is nevertheless possible to avoid this competition with proton reduction and favor this reaction. But you have to understand that, again, when you do CO2 reduction, you provide OH minus. So at the interface here, locally, you have OH minus, so you cannot avoid to make carbonate. But when this carbonate is going into the bulk of the electrolyte, reacting with a high concentration of protons, you generate CO2. So the question is whether you can recover this CO2 and put it back into the cathode. And that's what we have achieved. I have no time to also explain the details, but we have designed a specific cell using a bipolar membrane that allows equilibration of charges. We have an acid electrolyte. This membrane allows to have an alkaline anolyte. We don't need to have the same pH. And the interesting thing with this alkaline anolyte is that you can use an anode with non-noble metal instead of having iridium oxide or ruthenium oxide and so on. And as you can see here, with low flow rate of CO2 going here as a gas in this gas diffusion layer, as you can see, even in such a low pH, I mean something like, you see pH 1, we succeed to make 35% of ethylene and 20% of ethanol. So it's very interesting. And furthermore, we have been able to design a cell in which the CO2 that is being generated in the bulk electrolyte can be recovered in an indirect outlet and re-injected into the system. And the result is that we have almost, and this is a record value, something like almost 90% of conversion of CO2, because we could re-inject the CO2 into the system and use as much as CO2 as possible. Okay, so certainly I have no time to develop that. I can just tell you the principle. There is another strategy to avoid the carbonate problem, is to do two electrolysis. One is going from CO2 to CO, and then CO electrolysis to the product. And the reason for that is twofold. I mean, the first one is that there are good catalysts and solid oxide electrolyzers that allow to do carbon monoxide with very good yields without carbonate formation. And furthermore, the carbon monoxide does not react, the chemists can understand that well, does not react with hydroxide. So you have no catalyte degradation, no carbon loss, no carbonate formation. And we have been doing in the recent years very nice work with copper catalyst, and here you can see the result from CO reduction. We have a system, this is a long-term electrolysis, and now we reach, this is also a record, we reach 80% Faradic efficiency for converting CO into ethylene. So, okay, I stop here. Yeah, I wanted to show you where were the challenges, how you can address them with some success. It's nice to see that two British guys contributed to this work. Charles has now got he was a postdoc recently, he's got a position in Kiel University. And David decided to stay in France and develop a startup company on CO2 reduction. And I thank you for your attention.
Thank you very much, Marc. Very interesting.